Thanks for the introduction. Can everyone hear me? So, yeah, I'm Rixin, a 51 PECB fellow from UC Berkeley. I want to first thank KITP and the organizers for having me here. Today I want to cover two topics. One is late dust retention at the expanded magnetospheric truncation radius as a potential pathway to form these close-in planets. The other one is how this planetary system end up in broken resonant chains. But due to the limited time, my primary focus will be the later one because it's a new work accepted not too long ago. So Kepler planets, which I use to refer to sub-Neptunes and super-Earths, are the most common type of exoplanets. And they are also very social because they mostly are in these compact systems, like a few examples here. Now, if we quantify the orbital spacing of each neighboring planet by using the P outer over P inner, the distribution looks like this. The histogram, you may have seen this in quite a few literatures. And the histogram spread out nicely as a continuum, but there are also peaks to the right of 3-to-2 resonance and a peak to the right of 2-to-1 resonance with a trough to the left of 2-to-1 resonance. This is the so-called peak-trough asymmetry. Despite all these peaks, the fraction of pairs in or near resonance here with 3-to-2 and 2-to-1 are small. Only 10% of them are in this green zone. However, note that this is a gig-year-old sample. And if we go back in time, thanks to TESS, the fraction actually skyrockets, as shown in a work led by Fei Dai, my collaborator. And this figure shows the fraction of resonances as a function of age. And before 100 million years, the fraction, either in system or in pairs, are dominated by resonance, which means most planets in younger systems are in resonance. So, with this updated information, we can infer how this histogram looks like for younger systems. Simply, all planets should be in peaks. And now two questions arise. First, why most planets, they begin in resonance and in resonance chains? The short answer is, as we've seen in this conference, the resonance capture near the inner disk edge will put these planets into resonance chains. And second question is why they break, or what break these resonance chains? The short answer is dynamical instability. After disk dissipate, and they will break these peaks into continuum. And it may not be immediately intuitive how dynamical instability changed the histogram. Here is just a simple cartoon example. And for small planets in such a deep potential, the dynamical instability leads to orbital crossing and then major mergers. And the major merger here, the middle two planets merged, it gives you wider pairs, which means dynamical instability moves pairs from peaks to larger period ratios. And that's why dynamical instability smooths out this histogram. And now let's take a closer look at this entire scenario. Resonance capture happens when Kepler planets formed near the inner disk and then migrate towards the inner disk edge sequentially. And meanwhile, eccentricity damping during disk migration naturally offset the resonant pairs to slightly right of the exact integer ratio. So it naturally gives you these peaks to the right of these dashed vertical lines. And this scenario has been used to explain long chain systems like TOI 1136. FADI 2023 has used this scenario and conducted slow, short-scale migration simulation and produced a lot of TOI 1136 analog systems just by migration simulation. And here is one example. There are many, many of these examples, and these histograms are exactly from all these analog systems. Now, the question we want to address here are, for this analog system, if we keep evolving them, does they evolve into dynamical instabilities? And if so, do they produce this histogram and specifically all these fine structures, resonant fine structures? So what we did is we take these analog systems and then we keep integrating them without the disk. We were hoping for a show of cascade. However, after 100 million years, nothing actually happened. And this contradicts the time scale suggested by the latest observation. So this capture, resonant capture near the inner disk edge, works too well in this case. And all these systems, they are deeply locked in resonance. It's just too hard to break them within the right time scale. And as a frustrated theorist, we decided to ask a different question. So instead of identifying the mechanism seeding instabilities, we wonder, can we directly find the post-disk initial conditions that become unstable in the right time scale and also give this nice histogram and preserving the resonant fine structure in it. And we believe by doing so, the community will also better informed when they're looking for the seeder instability seeder mechanisms. And this time we use the TOI 1136 again as a blueprint, but we directly build TOI 1136 clones by replicating the best fit observed orbital elements and randomize them within 1 sigma of the best fit observed data. So the orbital plot looks the same, but what's the real differences between the analog system from migration simulation and the clones from data? The bottom figures shows the distribution of the amplitudes of resonant argument, which is a measurement on how deep these systems are locked in resonance. The smaller, the deeper they are locked in resonance. And as I mentioned before, the analog system, they are deeply locked, but unlike them, the clones, they are liberating much more than these analogs. So they are not deeply locked. So as you may have expected, if we integrate these systems by 100 million years, in typical simulations, the analog remain intact, but the clones systems, they will have instabilities. Now with the attack of the clones, the histogram finally spread out at 100 million years, at the time scale of 100 million years, matching the latest observations. And we got basic features like the 322 peak and 221 peak and the trough here. But we also have this bimodality in the continuum outside the peaks. And that is because our initial condition only has one orbital configuration. So if we diversify the post-disk initial condition by adding a little bit more little peaks and build the near resonant system in the same spirit, the histogram will look much better and much more like the observations. Besides the peak and the trough, we also have nice continuum in the histogram. And we also got 30% of them remaining in the first order resonance, well within the suggested range by observations. And we are also the first to propose that the reason for this trough is simply because the wide desert of the first order resonance ratios between 3:2 and 2:1. And our scenario also predicts for non-resonant planets, they are merger products, so they should be more massive than the resonant planets. And here is what we are showing the non-resonant the color, just making sure the color here. Here, the non-resonant has more massive tail than the resonant. And this is seen both in the controlled observation sample and in the simulations. But one more feature we identified is when you have mergers, they can sometimes also end up near resonance by chance, which then gives you this high mass tail in the resonant population and this slope change, which is not seen in the other one. And second, the signature of a long, rich history of instability is also encoded in the transit time variation data, leading to this broad non-zero KITP phase. To put it simple, if this distribution is wide, then it indicates a violent history, and it's both in the observed data and our simulations. So overall, our scenario can produce many of the observed properties, including the resonant fine structure in the histogram. The remaining open question is what actually seeds this 100 million year instability, which I hope to hear more ideas in a discussion or more talks. Okay, for the remaining, for 1 minute, I'll briefly touch on the dust retention topic. The prevalence of wide resonance and the fragile second order or sometimes three order resonant pairs, they require slow and short scale migration, which most likely happen in low density disk in late evolution stage. Also, meanwhile, the Kepler planets also show weaker dependency on host metallicity. This again favors layer formation in late time, as by that time the stars already gained their metallicity, has a fixed metallicity. So motivated by this in a series of 2 papers, we formalized a scenario to study the local dust size distribution evolution in global pressure maximum induced by the expanded truncation radius. And this is only possible in late time when m dot drops, the RT increase and the temperature become feasible for dust to survive and to accumulate. But I'll skip some of these and just show my summary as my time is up.
Ms. Rixin, questions?
Lauren Weiss, University of Notre Dame. Thank you for this interesting work. So one thing that I've seen in the past is that using the Bern model, Christophe Mordicini did something similar to what you showed of starting planets in very, very close period ratios, including many that were near resonance, and getting that period ratio distribution to relax toward the observed distribution. But that was at the time of the gas dispersal from the disk. So my question for you is, if you go back to your sort of your tuning of TOI 1136 and then your reproduction of that sort of broadened period ratio distribution, my question for you is, to what extent does the dissipation of the gas disk obscure our ability to understand the late stage properties of the disk in which these planets formed. In other words, as soon as this gas goes away and we don't have the damping anymore, the planets are gonna relax to that distribution. So can we really probe the physics of the late disk?
Thanks for the question. I think this latest observation that the fraction of systems are just resonant systems and the pairs are just so high between 10 and 100 million years indicates that the disk dispersal, the process, does not immediately destroy all the resonant chains. So it may plant some seeds, but I don't think that process isolated can or will fully explain what we observed in the population, in the later gigayear population. Yeah.
Hi, Sean Raymond, University of Bordeaux. So I have kind of a comment. So the model that you've developed is very similar to the one that we've developed over many years, you know, with previous, led by Andre Isidoro, called Breaking the Chains. And that was really built itself on previous work by people like Turkham and Papalouizou and you know, McNeil and Nelson and so on. And what Andre had found specifically in terms of the possibility that systems can go unstable late, you know, with a fraction of resonant chains that will go unstable, was that basically they go unstable on their own at a decent rate, and the likelihood of going unstable depends on two things. Basically, how compact the system is at the end of the migration phase, which itself is, you know, depends on the migration recipe and the disk properties, as well as the presence of external perturbers that can kick the system after the gas goes away. And so, at least in Andre's latest stuff, you don't need to invoke anything else. The systems just go unstable on their own at a reasonable rate. But the idea of, you know, what exactly does that is still of interest in connecting the dots, but just want to make sure that you're aware of all this.
Yeah, we definitely cite Isidoro a lot in our paper. But I also want to point out Isidoro, they focus on fitting the CDF of this histogram. So by doing that, you can ignore all these resonant fine structures. And I admit that by self-destruct, this system can be a good idea of breaking these resonant chains. But that's before this new observation information. So in Isidoro's paper, there are excess of very close, very tight resonant pairs, like 30% are in 7 by 6, 30% in 6 by 5, and then 30% or 20% 5 by 4. So a lot of them are very, very tight, leading to somewhat immediate destruction of the chains. So I would argue that we do have a slight different focus, and the scenario is a little bit updated compared to the old story.
Okay, so to keep the schedule on track, let's move to the detailed discussion further. One last question, quick question.
Yeah, this can be short. This is Ji Wang from the Ohio State University. If I understand correctly, you changed the depth, how deep those multiplanetary systems are in the resonant chain, and the result differs. But observationally, how do we know, what are the observational evidence that many of the multiplanetary systems, they are not deeply stuck in resonant chain?
This is actually a hard question for observation because there are not enough data for observation to tell how deep they are in the resonance. A lot of observations only have pure ratio data for, in high fidelity. So we only know they are near resonance. We don't know how deep they are in resonance for most systems. Yeah. Thanks.
Great. Yeah. Thanks, Rixin.